Hello everyone and welcome back to Moo Techie. It's great to have all the dairy technologists and future cheese scientists with us for another class. This is class 7 in our cheese technology series, where we continue to unravel the science behind great cheese. Today we're moving from our discussion on milk to a crucial ingredient, rennet, and its many substitutes. Let's start by defining what rennet is. Rennet is a complex of enzymes produced in any mammalian stomach to digest the mother's milk. It contains a proteolytic enzyme, which is a type of protease that specifically coagulates the milk. The most famous active enzyme in rennet is called chymosin, also known as renin. But there are also other very important enzymes in rennet, such as pepsin and lipase. Now, how is this rennet prepared? We'll look at both the traditional and modern methods for preparing calf rennet. In the traditional method, the stomachs of young calves are sliced, cleaned, and dried. Salt water and vinegar are then added to lower the pH of the solution. After several days, this mixture is filtered to produce a crude form of rennet. Incredibly, about 1 gram of this crude rennet can coagulate between 2 to 4 liters of milk. The modern method is more refined. It begins with the lining of the calf's fourth stomach, known as the abomasum. This lining is washed, dried, and cut into small pieces. These pieces are then macerated in water with a 4% boric acid solution at 30 degrees Celsius for about 5 days. Next, a 10% sodium chloride solution is added at 15 to 20 degrees Celsius for a few more days, resulting in a crude rennet extract. This crude extract contains an inactive form called prorenin. Acid is added to convert this prorenin into active renin. The solution is then treated with 1% potassium alum and 1% potassium phosphate, followed by filtration and clarification. Finally, the activated rennet is standardized for its activity, salt concentration, pH, and color before being packaged. Liquid rennet is preserved by maintaining a very high salt content, typically between 14 and 20%, and by adding preservatives like sodium benzoate and propylene glycol. Rennet powders are prepared by saturating the extract with sodium chloride. It's fascinating to note that in 1 kilogram of rennet extract, there are only about 0.7 grams of active enzymes. The rest is primarily water, salt, and sodium benzoate. And when we look at the final product, typically 1 kilogram of cheese contains only about 0.0003 grams of rennet enzymes. We can visualize the major steps in manufacturing liquid calf rennet. The process starts by removing and washing the lining of the fourth stomach. Any fat is scraped off, and the lining is cut into small pieces or strips. These pieces are soaked in a solution, which could be a 6% sodium chloride plus 2.5% boric acid solution at a pH of 5.4 for 3 to 5 days at 10 degrees Celsius. Alternatively, they could be macerated in water with 4% boric acid at 30 degrees Celsius for about 5 days, or mixed with Excelsior containing 10% sodium chloride to extract the enzyme. The prochymosin in the crude extract is then activated by acidifying it to a pH between 2 and 4.6. The solution is clarified by adding 1% potash alum followed by 1% potassium phosphate, and then it is filtered. This results in a clear yellow filtrate, free from any objectionable odor. It is then standardized for activity, pH which is around 5.7, and salt content around 20%, and a preservative is added. Finally, it is packaged in a light-proof container and stored at less than 5 degrees Celsius. Given the demand and various dietary restrictions, there are many sources for rennet substitutes. We can see a table comparing them. Original rennet comes from the fourth stomach of calves, and its active principle is chymosin. Bovine rennet comes from the fourth stomach of older bovine animals and contains a mix of pepsin and chymosin. Pepsin itself is sourced from pig stomach. Fungal rennet is produced from the fermentation of fungi, like Rhizomucor species, and its active principle is a protease. Finally, recombinant calf rennet is produced using microorganisms like E. coli, Aspergillus niger, and Chloromyces lactis, and it produces pure chymosin. There are also substitutes that are still of animal origin, just not from calves. These include chicken pepsin, bovine pepsin, and porcine pepsin. Moving away from animals, there are substitutes of plant origin. These are proteolytic enzymes found in higher plants, in their roots, fruits, leaves, seeds, buds, sap, latex, and flowers. 14 plant genera are known to possess milk coagulating activity. Examples include Carica papaya, Ficus carica, Withania coagulans, which is pineapple, Cucurbita pepo or pumpkin, Benincasa cerifera or ash gourd, and Cynara cardunculus and Cynara scolymus. However, these plant substitutes have a significant drawback. They often produce a weak curd, result in low cheese yield, can impart bitter and rancid flavors, and create an open texture in the cheese. Microbial origins provide another major source of substitutes. Many bacteria can produce coagulating enzymes, including alkaligenes, Serratia, Streptococcus, Corynebacterium, Escherichia, Bacillus, Lactobacillus, Thermoactinomyces, and Pseudomonas. Several fungi are also used, most notably Rhizomucor pusillus, Rhizomucor miehei, and Endothea parasitica. A modern and highly precise substitute is recombinant chymosin. This is produced using gene transfer technology, where the gene for bovine chymosin is cloned into a suitable production strain. Through fermentation, the enzyme is produced by this microorganism, isolated, and used just like calf rennet. Microorganisms like Escherichia coli, Cloiveromyces lactis, and Aspergillus niger var. Avamori have been successfully used for this production. Now let's look at the properties of chymosin itself. Chymosin is classified as an aspartate proteinase. Its molecular weight ranges from 30,400 to 34,000, and it consists of amino acid residues ranging from 276 to 274. It has a very high coagulation to proteolysis ratio, meaning it's excellent at clotting milk without excessive protein breakdown. 1 gram of pure chymosin can coagulate 22,700 liters of milk in just 30 minutes at 30 degrees Celsius. The stability of calf rennet is at its maximum when the pH is between 5.5 and 5.9. It's important to handle chymosin carefully. Photooxidation results in its inactivation, so exposure to light must be avoided. Chymosin can also be digested by other proteolytic enzymes, like porcine pepsin. Its activity decreases as the pH increases. A diluted solution of rennet loses its strength rapidly if stored for a longer period. The addition of substances like sodium chloride, citrates, phosphates, and hydrogen peroxide can delay rennet coagulation and reduce the firmness of the curd. The presence of other proteins like albumin, globulin, and peptone also tends to delay coagulation and results in a weak curd. Various processing treatments of the milk can influence the rennet coagulation time as well. Temperature plays a critical role in rennet activity. At temperatures below 20 degrees Celsius and above 50 degrees Celsius, rennet activity is very low. At temperatures between 21 and 27 degrees Celsius, the curd tends to be soft and jelly-like. At 30 degrees Celsius, the curds are firmer and do not break into dust on cutting. At temperatures between 33 and 36 degrees Celsius, the curds become tough and rubbery and release whey very slowly. Thank you for joining us for this detailed exploration of rennet and its many alternatives. Understanding these coagulants is fundamental to controlling the cheese-making process and creating a wide variety of cheeses to suit every need.